So we have seen in simple shear that the tensile stress of the same magnitude as the shearing stress, sigma is equal to Q, will develop at 45 degree to the shearing plane. By taking stresses on diagonal BD, now we have taken stress on the diagonal AC, and we have got that the normal stress sigma is equal to Q. Now if you consider this diagonal BD, we will get a compressive stress sigma is equal to Q. So we can say that the simple shear gives rise to tensile and compressive stresses across the planes inclined at 45 degree to the shearing planes, and the intensity of direct stresses being of same magnitude as the shearing stresses. So in planes inclined at 45 degree 45 degree to the shearing plane, there will be normal stress, and that the magnitude of this normal stress will be equal to the shearing stress. And in the case of this diagonal AC, it is a tensile stress sigma is equal to Q, and in the diagonal BD, it will be a compressive stress sigma is equal to Q. Okay. Okay, now we'll see what is shearing strain. Now you have seen this shearing stress has a tendency to distort the element to position A, B dash, C dash, D from the original position A, B, C, D. So this deformation can be expressed in terms of angular displacement and is called shear strain. So this phi is known as the shear strain. We are expressing the deformation in terms of the angular displacement. So here we can write tan phi is equal to opposite side BB dash divided by adjacent side, that is AB. So since this phi is very small, we can write phi equal to BB dash divided by AB. So this phi is known as the shearing strain. Okay. Now we'll see what is modulus of rigidity. Modulus of rigidity is shear stress divided by shear strain. So we are expressing shear stress by the letter small q and shear strain by the letter phi. So we can express, let us express the modulus of rigidity as G. So G is equal to Q divided by phi. Okay, so modulus of rigidity is expressed by the letter capital G, and it is the ratio of shear stress and shear strain. G is equal to small q divided by phi, where small q is the shear stress and phi is the shear strain. Okay, now we'll see what is punching shear. The punching shear is a failure mechanism in structural members like slabs and foundation by shear under the action of concentrated loads. So the action of concentrated loads on a smaller area in structural members will lead to the failure of the structural member by shear. This is known as punching shear. In most of the cases, this reaction is the one from the column acting against the slab, like this. If a column is there and there is slab adjacent to this column, in most cases this reaction is the one from the column acting against the slab. Eventually the slab will fail. The slab will fail or punch off along a punch cone. So one possible method of failure is that the load punches through the slab. You know how the punching machine works. You have used machines to punch holes on the paper. So the punching force required will be equal to the perimeter of the punching machine multiplied by the thickness of the member into the shear strength. So Some examples of the occurrence of concentrated loads on a slab are column, then a pad foundation, then wheel loads. So these wheel loads when act on a slab will act as large concentrated loads. As a result, this beam or the slab of the bridge may fail. So this same type of failure could also happen in another way, that is turning the structure upside down. That is, if a column is supporting a slab, we get a flat slab supported by a column where there is high concentration of shear force around the column head. When the total shear force exceeds the shear resistance of the slab will be pushed down across around the column, or this can be viewed as the column being punched through the slab. Okay, so this is a column supporting a slab, roof slab. So as a result of this concentrated load on the column from the top stories, the column will punch through the slab. So punching shear failure mechanism is observed in normal floor slabs, flat slabs, and in the foundation slabs below the columns. So it is observed in normal floor slabs, in flat slabs, and in the foundation slabs below the column. In pad foundations where weight and depth are not so critical, its effects are satisfied by providing sufficient depth. So how can you prevent this punching failure? We can provide columns with column head, and also we can increase the depth of the slab. So increasing the size of the column, etc., are some of the methods to prevent the punching failure in punching shear failure. So this will be the failure surface. So we can prevent this failure by providing heads, column heads, and also increasing the depth of the beam. So increasing the depth of the slab, increasing the column size, incorporation of drop panels, introduction of flared column heads are some examples or methods in order to prevent the failure of column by punching shear. Okay. So the punching shear will occur when there is concentrated load acting on a column which is supporting this floor slab, or it may occur in pad footings, it may occur in wheel loads acting on bridge slabs, or it may occur in a column which is supporting the roof slab. This column may punch through the roof slab, or here this column may punch through the floor slab. These are some cases of punching shear failure. Okay. Okay, now we'll see about Poisson's ratio. When a material undergoes change in length due to the action of some load, it undergoes changes of opposite nature in the lateral direction. So we are applying a load P in the axial direction. There will be increase in length in the axial direction or the linear direction, and there will be decrease in length in a perpendicular direction, that is in the lateral direction. So here this bar is subjected to a direct tension in the axial direction, so it elongates, and at the same time we can see its sides contract. So these are the changes in the lateral direction in a square cross section and on a circular cross section. The cross section will reduce to this one. Here the cross section will reduce to this one, while there will be increment in the longitudinal direction. So if we define the ratio of change in axial direction to original length as the linear strain. Now you know what is linear strain. It is change in length in the axial direction by original length, and lateral strain is change in length in the lateral direction divided by original lateral dimension. This is lateral strain. Now we can see that it is found that within elastic limit there is a constant ratio between this lateral strain and linear strain, and this constant ratio is called Poisson's ratio. So how can you write Poisson's ratio? Poisson's ratio equal to lateral strain divided by linear strain. Okay, now how do you know how we will denote this? It is usually denoted by 1 by m or mu. Poisson's ratio is denoted by 1 by m or mu. So for most of the metals, its value is between 0.25 to 0.33. 0.25 to 0.33, and for steel it is 0.3. So you must remember this value. Poisson's ratio for steel is 0.3, and for concrete it is 0.15. For concrete, mu is equal to 0.15. You must know this value. For steel it is 0.3. Okay. So Poisson's ratio for steel is 0.3. This value we have to remember. For concrete it is 1 to 0.15. For rubber, mu is equal to 0.5, and for cork, mu equal to 0. That is, when we increase the length, you are applying a force in the linear direction. In the lateral direction also there will be increase in length. That is the peculiarity of cork. So here mu is equal to 0. Okay. Thank you.